So hey everybody, this is Mr. Bells. I'm going to kind of give you a couple different lessons here in the same one. It's about two lines that we're going to call parallel now, cut by a transversal, and the relationships that exist from them. I've had some separate little internet videos that I've liked from other people that I put on there also. This one's going to be from me, and I'm going to try and do a couple different things. Here we go. In your student journals, if you could kind of go to those ones. We're going to start with section 3-2 on page 73. 3-2, page 73. So if you need to get that out, go ahead and do that right now. So the first thing I'm going to do is I'm going to talk about this thing right here. Is what happens now specifically. We've talked about two lines cut by a transversal. What happens if those lines are parallel? What happens if those lines are parallel? Well, it turns out that we can prove a lot of things, and I'll kind of go through this with you right now. Turns out that this angle right here, this angle 2 and this angle 6, if the lines are parallel, again, if we have parallel lines, and that's our conclusion, right? If the lines are parallel, then corresponding angles are congruent. So 2 and 6 are congruent. Now again, if this line right here was actually like this, and we had these two lines, then those two angles aren't going to be congruent. But if the lines are parallel, then they're actually going to be congruent. And that also means that this is true, right? So if angle 2 is congruent to angle 6, we know that angle 2 is congruent to angle 3, right? Because those are vertical angles, and the vertical angle congruence theorem says that for us. So if 2 is congruent to 6 and 2 is congruent to 3, then 3 must be congruent to 6 through transitivity, which means that I just proved this one right here. I just proved the alternate interior angles theorem, and that says that anytime that you have parallel lines and you have alternate interior angles, whether they're 3 and 6 or 4 and 5, that those two things must be congruent also. And then it says down here, there's this alternate exterior angles theorem, that must be true. Well, why is that true? Let's see if this makes sense. If I put a little box right here on this one, 6 and 7 are congruent by vertical angles, right? And 6 and 3 were congruent from the alternate interior angles theorem, theorem 3-2. Therefore, through transitivity, 3 and 7 must be congruent. Wait, those are corresponding angles. Look at that. So if 2 is congruent to 3 and 6 is congruent to 7 and 3 is congruent to 6, then through transitivity I can get 7 congruent to 2, and that's the alternate exterior angles theorem. And that's what we're trying to do now. We're just going to keep building these proofs from things that we know. Okay? So what else do we know? Let's flip it over here and see what this one says. This one says the consecutive interior angles. So first off, I want to circle two consecutive interior angles. So I'm going to do 3 and 5. And I'm going to ask you, do you think those two things are congruent? Okay, so my question, is angle 3 congruent to angle 5? And I'll get people that'll say yes. But the answer is obviously no. I mean, look at angle 3 is acute and angle 5 is obtuse, just from the general picture that I see right now. Now again, I can't assume acute and obtuse really from the pictures, but it's definitely not the same. So what is the relationship between 3 and 5? Well, let's see if this makes sense. 3 and 1, right? 3 and 1 are supplementary because they form a linear pair. So 3 and 1, so 1 and 3, when I add those up, add up to 180 degrees because they're supplementary from the whole linear pair postulate. And angle 1 is congruent to angle 5, right? 1 and 5 are congruent. That's the corresponding angles theorem that was on the page just before this. Corresponding angles are congruent. Well, if 1 is congruent to 5, then 1's equal to 5, and I can take, right, I can take any place there's a 1 and put a 5 in it. So that means I can take that 5 and shove that right there. And that means angle 5 plus angle 3 adds up to 180 degrees. So what do we know about these two things? Well, if they add up to 180 degrees, then they must be supplementary. And that's what the consecutive interior angles theorem says, is that consecutive interior angles are supplementary. They add up to 180. 4 and 6 are also supplementary. 2 and 8 are supplementary, and 1 and 7 are supplementary. But again, I want to make sure we're clear on this. That is only true, right, if the lines are parallel. Okay? So I'll make sure we're clear on that. Okay, so right here, it's going to say, hey, can I use some of these properties and do some of these things? It says, find the measure of angle 1 and 2, tell which theorem you used in each case. So if I want to know the measure of angle 1, I can say that angle 1 is 110 degrees because of the alternate interior angles theorem. I can say that 2 is now 110 because of the vertical angles theorem with angle 1, or I can say that 2 is 110 because of the corresponding angles theorem with those 110. Is that okay? And we'll go through some of those things, and then we get into stuff like algebra stuff. It's like, hey, what do we know about this? So one of the things that the videos talks about doing is putting O's and X's or O's and A's in your thing. So if this angle right here is a big one, we're going to put an O, we're going to put an O, we're going to put an O, we're going to put an O. O's stand for obtuse angles, A's, 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 and A's. A's stand for acute angles. And we know that an O is always congruent to an O, an A is always congruent to an A, and an O plus an A equals 180 degrees. Again, that's from one of the other videos that I put up. It's kind of a nice thing to be able to remember that that's true. So all I have to look is, now that I've labeled my O's and A's for obtuse and acutes, for the way they look. And again, this only works, one more time, only works if they're parallel, and those little arrowheads, right, mean that they're parallel. I can look at my two numbers that are in here. So I have an O and an O. Well, an O and an O means they're congruent, which means I can write x plus 12 equals 110 degrees. And go ahead and solve that. X equals 98 degrees. Again, not the angle, not the angle. X equals 98 degrees. And then I can go ahead and plug that back in there. Good deal? If I needed to. And if that's 110, then this one right here is 70 degrees, right? Are we good? So it just works through some of that algebra stuff, and hopefully that's beneficial. So that's section 3.2. That's if parallel, then angle relationships exist. Angle relations exist. And those angle relations are, there's a lot of them. Some of them are going to be congruent and some of them are going to be supplementary. And we just have to know that. So what the heck happens next is in 3-3, we've got all of these different proofs on that stuff and alternate interior angles. Ooh, this stuff right here. Watch this. So there's this key word that shows up in this converse, just like we had when we did conditional statements, converses, inverse, contrapositives. This converse shows up on all of these new theorems. This is on page 78. And you'll see a converse here, and a converse here, and a converse here, and a converse here. And there's all of these different things. So what the heck does that mean? This basically takes the ones from before, and these ones all prove lines parallel. Prove lines parallel. So this is saying, hey, if I got two lines that are cut by a transversal and these angles are congruent, then the lines must be parallel. So it basically took the stuff that went the one way before, and now it switches those two. By definition, that was what our converse was. Now it says over here, look, so I've got these two angles, right? Let me show you in another picture. This is 110, and this is 110, and I'm like, hey, are those lines parallel? So the first thing I'd say is, well, I don't have little extra arrowheads on those that make those parallel, right? Don't have that. I don't have this statement right up here. I don't have A is parallel to B. I don't have that written anyplace, right? So no extra arrowheads, none of that. But are those lines parallel? And the answer is yes. They have to be parallel because the alternate interior angles converse says that. Basically, if you have alternate interior angles and they are congruent, then the lines are parallel. And that works for the alternate exterior angles converse, consecutive interior angles converse. Now, be careful. This one right here, keyword, consecutive interior angles must be supplementary. Okay? So everything in 3-3 when you're reading through the books, and again, this video is kind of like 3-2, 3-3 combined. Everything in 3-3 is about proving lines parallel, things that prove lines parallel. So putting the word converse on the end of all of those alternate interior, alternate exterior, consecutive interior, all of those things help prove lines parallel. So what else proves lines parallel? This one down here at the bottom. This says there's a thing called transitivity, which we know, right? Transitivity is a three-way thing that says if 1 and 2 are equal, and 3 are equal, then 1 and 3 must also be equal. Well, now this is called a transitivity for parallel lines. It basically says this, that if P is parallel to Q and Q is parallel to R, then we can jump all the way from P to R. Okay? So as you finish off in 3-3, you'll have things like this, and we'll have lots of questions that say, can you or can you not prove that lines are parallel? Okay, so this would be an example of this one down here. Can I prove lines are parallel? Well, these two marks are congruent, and those are corresponding angles. So I would use the corresponding angles theorem converse to prove that the lines are parallel. Awesome. Number 4, these are vertical angles, and I'll ask you if you flip back in your book, is there any vertical angles theorem converse? And the answer to that is no, there isn't one. And you can obviously see that M and N, I can't prove that they're parallel. They might look parallel. But there's no angle markings whatsoever down here on this line, which means I technically could tilt it any which way possible, which means I can't guarantee that they are parallel. Okay? So this one down here, can I prove anything about the lines that are parallel? And you can see one more time, R can be twisted and N can be twisted, so this is a no on that one. And this one right here, S, I can twist that in the middle so that doesn't stay fixated by anything. But I can see that this angle right here and this angle right here are congruent. Those are alternate exterior angles. So I can say yes that M is parallel to N by the alternate exterior angles theorem converse. Okay, so those are some of the different ways that we can do it. So the first thing that we talked about was if the lines are parallel, then these angle relationships occur. And then there's the whole converse, the switching those around, that if the angle relationships actually occur, then the lines must be parallel. So we just got to keep straight those two things. Are we trying to prove the angle relationships, or are we trying to prove the parallel lines? Kind of like which came first, the chicken or the egg. Hopefully this was really helpful. Again, we'll have problems for you guys to try in the Big Ideas Math. This was video 4-3-2, 3-3 kind of combined. Take a look at the other ones that I put up from YouTube. They do a pretty good job on some of those things. So this is a little bit more algebra practice on some of those ones too. Awesome, thank you. See you guys later.